Hello, we are the CSU Tolmar Polymerization Optimization team, and I am Surya, and I will be kicking off our presentation. First, for some project background, PLGA is a versatile biodegradable polymer in the biomedical engineering industry, used for a variety of applications ranging from biomedical devices to long-term drug release injectables. We have been tasked with developing an in-house production process of PLGA for Tolmar. With that came a couple of objectives, including producing 50 kilograms per year, a target molecular weight of 50 kilodaltons, as well as a final polymer composition of 50/50 glycolide to lactide. We modeled this process using MATLAB and SuperPro. For our project timeline, we first started off with a research phase where we looked into the theoretical chemistry behind the reaction and synthesis of PLGA, as well as methods of executing that reaction and potential equipment. This led to our process synthesis phase, where we looked at different design pathways of how to produce PLGA and what was best for our project needs. This led to our initial model phase, where we built our model in MATLAB and SuperPro, and led next to our process optimization phase. Here we looked at the sustainability as well as the safety of our process and implemented process controls to make sure we reach our safety and quality marker goals. And this finally led to our project feasibility phase, where we completed our techno-economic calculations to see, is this process actually viable for Tolmar? And this is all leading up to E-Days. So for our market and competitive analysis, PLGA is a highly demanded product because of all of its versatile applications. Currently, the global market value is 1.2 billion USD and is projected to reach 2.3 billion USD by 2033. Currently, Tolmar does not produce or sell any PLGA, although it uses the polymer for long-term release drug injectables. Currently, the top competitors include Evonik, Corby, Mitsui, all quoted for $700,000 for 50 kilograms annually, but our goal is to produce PLGA to offset the cost of purchasing it from external sources instead of selling it ourselves.
Hi, my name is Roman, and I'm going to be talking about the budget for our project. We were given no real money for this project, and so we were unable to do any experimentation for this project. And so we decided to set a goal for our process entirely theoretically, that we wanted to produce 50 kilograms of PLGA in under $700,000 per year, which was one of the quotes given to us by one of the competitors. Right now, the total capital cost for our process is $2.1 million, and that is with the assumption that we are buying all new equipment. For our process synthesis tree, we have the first row is going to be the different reaction types we could have went, or process types. And we chose an in-solution batch reaction because we want to control the reactivity of glycolide and lactide, as glycolide is more reactive than lactide. And also, we chose the in-solution batch because it also made more sense for the scale of our process. For the reactor, we chose a vacuum jacketed reactor because it allows for easier temperature control of the reaction, and the catalytic membrane reactor, which is very expensive, and the membranes are also fragile as well. We also decided to choose precipitation with drying, as centrifugation is a separation technique, but precipitation and drying allow for separation and purification in our process. We also chose solvent recycling because this made our process more sustainable, whereas refrigeration, we would just be selling the solvents, and heat exchangers, we would probably burn them off, and this would just hurt the sustainability of the process. For our simplified process flow diagram, as you can see here on the left, we have our reactor, which is where the initial polymerization happens. This will be modeled using MATLAB. Coming out of that reactor, we're going to have PLGA, unreacted monomer, some catalysts and solvents, and these go into precipitation vessel. PLGA with the unreacted monomer and stannous octanoate are going to be precipitated out of the solvents. The solvents will then be flowed into storage tanks and stored until we have enough to run them through the distillation columns to purify the solvents and reuse them in our process. Coming out of that precipitation vessel on the bottom is PLGA, unreacted monomer, and the catalyst. This will go into a vacuum filter where we will filter out the unreacted monomer. And then PLGA and stannous octanoate will be flowed into a dryer which will then purify the product as much as possible before we have it ready for final steps. And then this will all be modeled in SuperPro.
Hi, I'm Andrew, and the two main design specifications that we can optimize in PLGA production are first, keeping a true 50-50 lactide to glycolide ratio, which is critical because it directly controls degradation time. Um, and then second, targeting a molecular weight around 50 kilodaltons. Helps maintain polymer stability. These quality markers tie back to performance in downstream pharmaceutical applications. And importantly, using an in-solution polymerization method gives us the control and scalability needed to reliably hit these specs. So the core elements of our reactor model are the initial polymerization tank, where we combine lactide, glycolide, catalyst, solvent, and initiator under controlled temperature to generate the initial product stream. The ratios of all these inputs directly affect the molecular weight distribution and the ratio of lactide to glycolide. And that stream then feeds into the precipitation vessel, where methanol drives PLGA out of solution, also affecting molecular weight distribution. Our optimization found that reaction rate constants Ki and Kp affect the molecular weight distribution, and thus our target of 50 kilodalton PLGA. When initiator is faster than propagation, we see a narrow molecular weight distribution. When initiation is slower, the distribution broadens. This tells us that our reaction should include a higher catalyst and initiator concentration. One limitation of the model is that it doesn't yet capture dipolymer formation, but just this week, we've made a breakthrough in a version of our model that adds that layer of complexity.
My name is Hans, and when designing this process, one of the greatest safety risks that became apparent was the solvents, being toluene, acetone, and methanol. With these solvents posing an inhalation hazard via the vapor pressure, the flammability hazard by their reactivity, and with the quantity used at various points in the process, accidents with the solvents would have the highest frequency and would also be of high consequence. Therefore, when designing the process, it was taken into consideration for the creation of vent points to close containers to avoid releasing the atmosphere, along with having the storage in a separate location, away from the process equipment and personnel when possible. That was just one of the safety improvements made during the creation of this process. By the inclusion of control systems and emergency response systems as seen in the PNID, operators should feel safe at any location in the process. It is, while not immediately necessary to understand the PNID, you can see general trends of the design. On the left is the reactor and the control system, which is then followed by the downstream processing in the bottom right. In the upper right are the distillation columns, which allow for solvent recycling to improve the project's sustainability.
My name is Ridge, and I'll be going over some of the sustainability design impacts of our project. So as of right now, our greatest strength is the environmental sustainability, and this is primarily due to our solvent recycling columns. Having solvent recycling columns allows us to reuse the solvent we use for our process. So instead of having to sell it to an outside vendor to dispose of it, or instead of disposing of it ourselves, we could reuse it, which will help reduce our economic footprint or our environmental footprint. Further, it would reduce the amount of solvents that we need to purchase from an outside vendor, which would further help reduce our carbon footprint. Something that we need to improve is the societal impact of our project. As of right now, PLGA improves the quality of life for all patients. Instead of having to get an injection every week or every 2 weeks, you can get an injection every 2 months or 3 months. But that's about it for the societal impact right now. So that's something that could be improved on. If you look on the right half side of the screen, you can see our product stewardship metrics. So our previous design is in blue and our new design is in red. And you can see that we've made the greatest improvements in the social responsibility and the strategic commitment of our project, while not making too many improvements in the value chain management of our project. For the techno-economics of our project, this is pretty much describing how viable our project would be and if it is a good idea for Tolmar to do this economically. You can see our cash flow on the right. So for the first year, we're going to be losing a little bit of money, and this is mainly because we have to purchase all new equipment. But after the first year, we start to make some money, which is good for Tolmar. The return on investment of our project is 14.58%, and the payback period is 3.06 years. And it should be noted that if Tolmar decided they wanted to make 100 kilograms per year or even 200 kilograms per year, the process would become more economically viable. So in conclusion, we created an in-solution process for the production of 50 kilograms of 50/50 PLGA per year. Next, we created a MATLAB and SuperPro model to accurately represent the process and all the downstream processing of the process. Next, we optimized the process for sustainability and safety to help make our project safer for the workers and more sustainable for the environment. And lastly, we investigated the techno-economics to determine whether the process was viable or not, and it was determined that the process should be viable. Thank you. We are Team Tolmar, and thank you for listening.